Today we are talking about the Diels-Alder reaction, which I introduced last time. This was discovered 100 years ago, and it involves the reaction of a molecule that we call a diene. It's a conjugated diene or a 1,3 diene, and then an alkene or an olefin or a dienophile, the molecule that reacts with the diene. And we'll talk about what the orbitals are doing here. We'll talk about which one is thought to be the nucleophile and which one is thought to be the electrophile. In general, the dienophile is the electron-poor molecule. But they react together, and this reaction is more complicated and at the same time more simple than a reaction that you've dealt with previously. There are 3 pairs of electrons involved in this reaction. You've got the pi bond between carbons 1 and 2, the pi bond between 3 and 4, and then the pi bond between the 2 carbons of the dienophile. And you make a new molecule that has a new 6-membered ring. You make 3 new bonds, one between carbon, and how we number the carbons isn't necessarily important. I think to keep things straight, we'll do, oh man, I screwed it up again, didn't I? All right, well, whatever. We'll have a new sigma bond between orange 1 and purple 1, a new sigma bond between orange 4 and purple 2, and then a new pi bond between 2 and 3. That's a 6-membered ring. And so the first important thing you need to know about the Diels-Alder reaction is that the product is always a cyclohexene. All right? Now, as we've been learning to do synthesis, I've been showing you how you can look for structural patterns in products that can trigger in your mind ways that you could have made the molecule. For example, a 1,2-vicinal dibromide, you now know from chapter 10, you can get from an alkene. In the same way, I want you to be able to see and be familiar with the idea that if you see a cyclohexene, you be thinking, I could have made that through a Diels-Alder reaction. And this reaction adds to the list of carbon-carbon bond-forming reactions that you've seen before. But it's fancier, right? The only one we have so far is a reaction of an acetylide nucleophile with, say, an alkyl halide in an SN2 reaction to get a new sigma bond. But here in the same molecule, in the same reaction, we're making 2 new sigma bonds and a pi bond. I pointed out last time that we lose 2 pi bonds, we lose 3 pi bonds, but we make 2 sigma bonds and a pi bond. Overall, because sigma bonds are more stable than pi bonds, the reaction is exothermic. All right. And I've shown 2 products. Notice the stereocenters that get made when we do the Diels-Alder reaction. Of course, whether or not you make stereocenters is going to depend on the structure of your diene and of the dienophile. But if you look at what we did, I'm going to highlight in pink, maybe green, I don't know. Pink and purple show up the same on the screen. So I'll highlight in green all of the stereocenters that we form in this reaction, 4 of them. Now it just so happens that this is a meso compound because the molecule is not chiral. We have a plane of symmetry that goes in between atoms 2 and 3 and between purple 1 and 2 and coincides with this single carbon that's sort of above the cyclohexene ring. Same thing here. Both products are not chiral. Nevertheless, these 2 products that we've made are not the same. Notice that in the product on top, the hydrogens are wedges, and they are on the same side of the new 6-membered ring that I made with this carbon that's the carbon in the middle from our cyclopentadiene. Whereas in the product on the bottom, the 2 hydrogens are dashes. They are on opposite sides of the 6-membered ring as that carbon that was in the middle on cyclopentadiene. So these are two cis/trans type isomers, and therefore they are diastereomers of each other. Remember, we only have two kinds of stereoisomers. If two molecules are stereoisomers, they're either enantiomers or diastereomers. These aren't mirror images of each other, but they're stereoisomers, so they have to be diastereomers. Yes?
Now, do each of these have their own endo and exo conformations?
Okay, you've read the word exo and endo, and these are terms that actually have to do with what kind of diastereomer we're looking at. Okay, we can actually talk about that now. The chemists have. It's almost as though we don't have enough terms, right? We always need more terms. I talked about one of these as having a cis relationship between the protons and this, what I'm calling the bridging carbon, the carbon that bridges 4 and 1. Whereas the one on the bottom, the protons are opposite, on the opposite side of the 6-membered ring from that bridging carbon. The terms endo and exo are actually going to refer to that. So just to be, while we're talking about it, we'll come back to it again, but the diastereomer on top is called the endo diastereomer. And the reason you can tell it's the endo diastereomer is you compare the location of the two carbons that were attached to carbons 1 and 2. I'm talking about the carbons with the ketones. You look where they are they dashes or wedges? And then you compare them to the bridge carbon on the diene. Okay, that's this carbon 5. Here, the two ketone groups, the wedges, are on opposite sides of the 6-membered ring as that bridge carbon. And so for whatever reason, we call that endo. The one where the ketone carbons are now wedges and on the same side of the ring as that bridge carbon, that's called the exo diastereomer. It's generally thought, and in a lot of cases true, that the endo diastereomer is preferred over the exo diastereomer. There's some debate in the literature as to why that is. And we won't worry about it in any level of detail in this class. I will want you to be able to discern between the endo and the exo diastereomers when that's possible. And we'll go through some examples of that a little bit later. Does that sort of answer your question? Yeah? Okay, go ahead.
So what makes it endo is that it has like the dash with the exo and the wedges?
Well, endo and exo, like cis or trans, are relative terms. So what makes it endo is the fact that this, I need another color to highlight the issue of endo versus exo. We'll go blue, only that looks somewhat purple. So okay, back to blue. The issue of endo is the relationship between these carbons and this carbon. Okay, are those substituents from the dienophile or olefin, are they on the same side or opposite sides as the bridge carbon?
So would you say you can think about it as like E and Z?
Is it like E and Z? Is it like cis or trans? Yes. Though endo means they're on opposite sides, exo means they're on the same side. I was going to tell you a mnemonic device of, O stands for opposite, but then I realized that both of endo and exo end in O. So the best I can do is if you keep the bridgehead carbon up, then the substituents on the diene are down, endo is down. It's not really great, but it's maybe the best you can do. But it's a relative thing, right? It's not that these are dashes, it's that they are dashes while this is a wedge. It would also be an endo product if this was a dash and these were wedges. Yeah?
And it has to have a bridge carbon to that.
Does it have to have a bridge carbon? It's certainly easiest to pick endo versus exo when it has a bridge carbon. It doesn't have to be. And I can show you some examples of that a little bit later. What else? Yeah?
Will we ever like see a molecule where you have the dash and the wedge?
Will you ever, where, on the stuff that came from the diene?
Like if you have a dash and then a wedge.
Over here? Right, so you can think of many complicated situations where it would be impossible to tell whether a molecule was endo versus exo. For example, not in this molecule, but I will do an example of this later. If you used a dienophile where the substituents were trans to each other, then in the product, one of these is going to be a dash and the other is going to be a wedge. And in that case, you can't tell endo versus exo anymore. Yeah. In fact, it's a favorite question in OCHEM PhD dissertations when somebody talks about a Diels-Alder reaction and calls this as the endodiastereomer. And it's not really clear why they called it that way. It's a favorite question for a professor to say, why did you call that the endodiastereomer, right? Usually say it exactly like that. Anyway, so yes, there are situations where you can't choose endo or exo. I saw another hand. Yes, go ahead.
Can we draw this as a chair conformation?
Could you draw this from the side in a chair-like conformation? Sure. Are you asking, will I? No. Yes, I will. But let's answer this question first.
So what exactly makes a dienophile a dienophile? How do we decide which one we have to do some decision?
So how do you make it, what makes a dienophile a dienophile? It needs to have two characteristics. It needs to be an olefin or an alkene, and it should generally be electron poor. We'll say some more about that too. But since Miriam asked, I'm going to draw the molecule from the side. I warned you didn't want to see this, but now we are going to do it. All right. So our view from the side would look like this. Here's carbons 2 and 3, orange 2 and 3 of the section that used to be the diene. There's carbons 1 and 4 of the section that used to be the diene. Here's the new pi bond between 2 and 3. Here's the new sigma bonds with the portion of the molecule that's used to be the dienophile. Here's purple carbons 1 and 2. There is the cyclohexene core. The bridging carbon 5 needs to come up from 4 and 1. And so the best way to draw that is just like this. That bond's in the back. Now on carbons 1 and 2, I need, at least as I've drawn for our endodiastereomer, the protons need to be up, so that would be here. And then the other carbons need to be down, so that would be here. That's another, that part's hard to draw. Let's see, 1 and 2. 1 and 2 are each bonded to ketones, which are each bonded to something else. So yeah, that's sort of how I would draw the product. It's not really in its chair conformation, but yeah, sort of. Okay, maybe I'll highlight some things. Oops. This portion used to be the diene. This portion used to be the dienophile. The relationship between this carbon and these two groups is how you determine endo versus exo. And these 4 carbons are the stereocenters. And then we could do a similar drawing of the endo or the exodiastereomer, this would just involve, and to save time, I'm going to copy and paste. I know you hate that. So protons are down here, carbons are up, here are the ketone groups. That's maybe the best we can do. And this side view sort of helps you see more easily the relationship between the endo and the exodiastereomers. You can see more clearly that the blue groups on what used to be the dienophile are on the same side as that bridge carbon. All right, other questions? Yes?
Will the oxygen groups always be pointing opposite to each other?
The oxygen groups, will they always be pointing opposite each other? These groups here are optional. They come with this molecule because they were on the dienophile to begin with. We'll swap out all kinds of dienophiles. We'll swap out all kinds of groups. So these oxygens may or may not be there. Others? So let's make it a little bit simpler before we start talking about what the orbitals are doing in this reaction. Let's just use a very simple diene. Let's use the diene that's drawn here, 1,3-butadiene. Last time we talked briefly about the fact that 1,3-butadiene sort of has two different conformations that are conjugated where the pi bonds line up with each other. You've got the S-trans conformation where carbons 3 and 4 are pointing away from carbons 1 and 2. And then you have the S-cis conformation where carbons 3 and 4 are pointing towards carbons 1 and 2. We talked about how rotation around the bond between 2 and 3 is somewhat restricted because doing that brings the pi bonds out of alignment and breaks resonance. But we also talked about how the S-cis conformation takes these protons that are pointing inward on carbons 1 and 4 and bumps them into each other. So the S-cis conformation is less stable than the S-trans conformation. Nevertheless, the S-cis conformation is required for the Diels-Alder reaction. And so dienes that are more constrained to be in an S-cis conformation are more reactive in the Diels-Alder reaction. As an example, cyclopentadiene is a great diene in the Diels-Alder reaction because the bridge carbon 5 forces the molecule to be in that S-cis conformation. But let me show you a simple Diels-Alder reaction between 1,3-butadiene and then this olefin. Why didn't we start out with this one? Well, this one was not the one that Diels and Alder discovered, nor is it a particularly efficient one, but it does illustrate more simply what's going on. So you have your diene and you have your dienophile. In the reaction, you make a 6-membered ring. These are the bonds that you make. These are the carbons that used to be in the diene, and these are the carbons that used to be in the dienophile. And if you can follow that through, you already have got a lot of what's important in the Diels-Alder reaction. Now, as I said, there are 3 things going on at once. If you want to push arrows for the Diels-Alder reaction, one of the ways you can do that is this. 3 arrows at once. You need to show the formation of the new sigma bond between carbons orange 1 and purple 1, the formation of the new sigma bond between orange 4 and purple 2, and the formation of the new pi bond between orange 2 and 3. However, it's not at all clear where you should begin and end. That is, I chose to start by drawing my arrow for the pi bond between 3 and 4 attacking carbon 2, and the pi bond between purple 1 and 2 attacking 1, and then the pi bond between 1 and 2 shifting over to form a new bond between 2 and 3. It would have been entirely okay, however, for me to draw the reaction this way. Either of those are perfectly acceptable. And the reason for that is that this reaction's a little bit more complicated than would be suggested by the arrows. So let's dive into what's going on with the reaction. Let's consider the orbitals, the HOMO and the LUMO, of both of these molecules, all right? To do that, we'll need to remind ourselves of what the pi system of 1,3-butadiene looks like. All right, so if you recall, we have four, erase HOMO and LUMO. For 1,3-butadiene, we have 4 pi molecular orbitals that you've now seen previously. One of them is where, and we're just gonna draw, I'll draw the carbon skeleton of the diene, and then we'll just draw the top lobes just to keep everything clear. We're looking down at this molecule from above. We're just looking at the top lobe of the pi system. The plane of the page represents the node, and we're just looking at the top lobe. For the pi 1 orbital, all the top lobes are with the same wave function sign, right? You saw that before last time. This is not new, okay. So for pi 2, we expect there to be 1 node. That's going to be right in the middle between carbons 2 and 3. So we expect to see something like this. For pi 3, there will be 2 nodes. So we expect to see something like this. Whoops, there we go. No. And then for pi 4, we expect to see 3 nodes in between each of the atoms of the diene with a change in wave function sign in between each atom. And then we know that there are 2 pairs of electrons involved in this pi system, 2 here and 2 here, so we could therefore conclude that pi 2 is the HOMO and pi 3 is the LUMO. All right, that should be a bit of a review, but that's a summary of what we're seeing for the diene. Now let's look at the dienophile. That's a pi bond. The HOMO of the diene looks like this. It looks like a pi bond, and again, we're just looking at the top lobe of the pi bond. So that's the pi, and then the LUMO is the pi star, which has a node in between carbons 1 and 2 of the alkene or the olefin, a change in wave function sign between those 2 atoms. That's sort of what we would see. And for the dienophile, the LUMO is the pi star and the HOMO is the pi bond. All right. Now, one thing I want you to notice is the similarities between the HOMO of I want you to notice similarities between the HOMO of the diene and the LUMO of the dienophile. What similarities do you notice between those two? Go ahead.
I guess they're both half one thing and half the other.
Right, they're both half one thing and half other. They both have one node. They both have, if you compare the carbons on the ends, compare orange 1 and 4. 1 and 4 have opposite wave function sign, right? We might call this orbital anti-symmetric, meaning it's got mirror symmetry, only the wave function sign switches, right? If the node is the mirror plane, then what's up here is a reflection of what's down here, except the wave function sign is opposite. That's what we mean by anti-symmetric. Similarly, the LUMO of the dienophile, that pi star, is also anti-symmetric, meaning that carbon, the wave function sign on carbon 1 is opposite the wave function sign on purple carbon 2. So the LUMO of the dienophile is matched in symmetry with the HOMO of the diene. That's important because it explains something about how this reaction happens. So with that in mind, let's take a different view of this reaction. I'm going to draw carbons 1, 2, 3, and 4 of the diene sort of on its side. We're sort of tilted looking at the diene on its edge. This is 1, 2, 3, and 4. And now we're going to draw what that pi 2 highest occupied molecular orbital looks like. We're going to draw this schematically with sort of p orbitals on each of the carbons, 1, 2, 3, and 4, even though we understand that this is actually a fully delocalized orbital. The node is going to be between carbons 2 and 3. And then let's see, we'll put blue lobes here and red lobes here. And then in the back, you've got a red lobe here, a red lobe here, and a blue lobe here, a blue lobe there. All right, you got that idea? We're looking at the molecule on its side. There's a node between orange 2 and orange 3. There's a lot going on there, and I'm sorry for how much everything's sort of overlapping. Now I'm going to draw that, the olefin or the dienophile sort of on its side. We're looking at it on its edge, so I'm going to draw in the hydrogens that are implied but normally not shown on carbons 1 and carbons 1 and 2. Now I'm going to draw the pi star. And as with our drawing above, we've got a switch in wave function sign or a node between carbons 1 and 2. Now, I want you to observe as I bring, and let's see, this is the HOMO of the diene and the LUMO or the pi star of the olefin or the dienophile. The fact that both of them are anti-symmetric means that as I approach these two molecules, the portions of the orbitals on carbons on orange 4 and purple 2 line up with the same wave function sign at the same time as the portion of the orbital on purple 1 and orange 1 line up with the same wave function sign. In other words, I get productive bond forming overlap between 2 and 4 at the same time as I get it between 1 and 1. Their orbital symmetries are matched, so HOMO can attack LUMO. Now this is totally different in some ways to something you've seen before. In previous reactions like the SN1 reaction, when HOMO attacks LUMO, the HOMO's on one atom, the LUMO's on, and you attack the LUMO at a specific spot on another atom and you make one bond. Here, in this reaction, the HOMO is on multiple atoms and the LUMO's on multiple atoms. And so what we have just shown you is what happens to one of the pairs of electrons in this reaction. The electrons in this, the HOMO of the diene, attack the LUMO of the dienophile. Okay? As you can see, that's not the whole story because you've got 3 electrons involved in this reaction. We've just talked about what happens to one of them. We're not going to do this, but after class, if you want to modify this drawing, you should be able to see how now the HOMO of the olefin, or the dienophile, is mirror symmetric. The wave function sign on carbons 1, purple 1 and 2 are identical. And you should be able to see how the LUMO of the diene is also symmetric in that the wave function sign on carbons orange 1 and orange 4 are identical. So you should be able to see how we can do a similar drawing like this that would show the orbital lobes on 1 and 2 of the HOMO of the dienophile matching up with same wave function sign, the orbital lobes on carbons 1 and 4 of the diene. Okay? Does that make sense? That's where the other sigma bond comes from. So we get one sigma bond from the HOMO of the diene attacking the LUMO of the dienophile. We get another sigma bond from the HOMO of the dienophile attacking the LUMO of the diene. And then, interestingly enough, we get the pi bond from this pair of electrons in the pi 1 orbital. As the reaction proceeds, notice that carbons 1 and 4 become sp3 hybridized. They're no longer involved in the pi system. So these electrons don't actually do anything. They just stay where they were, only now they're only between carbons 2 and 3. Because carbons 1 and 4 are no longer part of the pi system. Okay? So you can see that our picture of arrow pushing accounts for all the bonds that form, but it doesn't really account for what the orbitals tell us is actually going on in the reaction, which is HOMO of the diene attacks LUMO of the dienophile and vice versa. And then these electrons that used to be delocalized across orange carbons 1 through 4 are now just only between 2 and 3. Yeah?
So would it be correct to draw that with 6 single-headed arrows?
Could you draw this with 6 single-headed arrows? I've never seen anybody do that. The reason you don't is because the orbitals tell you it's always 2 pairs of electrons that are doing stuff. So a single-headed electrons would indicate that it's more complicated than that, and there's not evidence for that. Okay, what else? Yeah?
So how does this work with like the star orbitals and things along orbitals? Like, it seems like when you, like previously when we had put electrons into a Pascal orbital that breaks the pi.
Right. So how does this work with like breaking bonds? Well, in some ways it accounts for it, right? Because I told you in the reaction, we lose the pi bond between 1 and 2, That's consistent with filling this pi star orbital. And of course, these electrons that go from HOMO and attack the LUMO form a new sigma bond, but you do break the pi bond. In a similar way, the pi electrons here attack the LUMO there. That can account for breaking of one of the pi bonds of the diene. So yeah, it's a little bit tricky to think of it in the traditional way, where attack of HOMO attacking an antibonding LUMO results in the breaking of a single bond. In part because with the diene, these empty orbitals are not just like a star orbital. They don't correspond to just one bond. They're delocalized over multiple atoms, and that's why this is a little bit more complicated than that. Okay, what else? All right, so a lot of stuff going on at once. This reaction is a concerted reaction, and there are stereochemical consequences to concerted reactions. That means that the stereochemistry of the diene and the alkene starting materials must be reflected in the stereochemistry of the product. So let me give you an example of that. We will use the same 1,3-butadiene, but this time we will use a different olefin. Here we're going to use an olefin that has two non-hydrogen groups cis to each other. I will continue to number the carbons. That may or may not be useful to you. 1, 2, 3, 4. 1 and 2. In the Diels-Alder reaction, which we would add heat to make this happen, we can push the arrows to show the formation of the new sigma bonds and the new pi bond. The product of a Diels-Alder reaction is always a cyclohexene ring. These are the bonds that you form in red. I want you to notice that the two groups that are cis to each other on the olefin must continue to be cis to each other in the cyclohexene ring. Always. Notice, by the way, that we are avoiding all kinds of issues by the choice of our products. And I just erased some stuff. We've got some symmetry. Carbons 1 and 2 are identical. Orange 1 and 4 and purple 1 and 2 are identical to each other. The molecule itself is not chiral, even though these are stereocenters now on the portion of our molecule that used to be the olefin. It's often helpful when you see a Diels-Alder product to identify the carbons that used to be part of the diene versus the olefin or the dienophile. The easiest way to do this is to focus in on where the pi bond is in that 6-membered ring. Those are automatically atoms 2, orange 2 and 3. If you can figure that out, then orange 1 and 4 follow, and then carbons 1 and 2, purple 1 and 2 follow. But the important part is the blue substituents on the olefin were cis to each other. In the product, they are still cis to each other. It has to be that way. There are no endo versus exo issues here because there's no bridging carbon, there's no non-hydrogen things on carbons 1 and 4. Of course, if you simply changed the stereochemistry on purple 1 and 2 and had the carboxylic acid groups be trans to each other, then they would necessarily be trans to each other in the final product, which we'll draw in just a second. 1, 2, 3, 4. Again, you can push arrows in the Diels-Alder reaction like this. Again, the product is a cyclohexene ring. Again, you can identify the atoms that used to be part of the diene. and that used to be part of the olefin. And then it's important that the two carboxylic acid groups that were trans to each other in the olefin starting material continue to be trans to each other here. Now, is that product chiral? You thought you were done with questions like that. You were not. Is that product chiral? Yes, it is chiral. It has no mirror plane of symmetry. This, you might think that's a mirror plane of symmetry, but do you see how this carboxylic acid group is a wedge, whereas this one's a dash? Molecule's chiral. The starting materials, however, were not chiral. So you have to get both enantiomers. The other enantiomer would look like this. And you have to get both of them. The reason you have to get both of them, and I can show you where the other enantiomer would have come from. Here's our diene. Here's our olefin. If the diene approaches the olefin this way, and we start to form new bonds here, then we get the product shown above. If, on the other hand, the diene and the olefin approach each other via one of a couple of different possibilities, we'll get the other enantiomer. Sorry, I erased the pi bond and now I'm having a really hard time drawing it back in there. There it is. If the diene approaches the olefin from the other side, we'll get the product shown above. In contrast, so that's one way. Alternatively, we could get the same product if the diene approaches the olefin from a slightly different orientation. So if we have the carboxylic acid group oriented here, that will give us this product. The idea is that these dienes and dienophiles are flat molecules. They have identical faces, and so they can approach each other this way or this way, and that's how we get the other enantiomer. So the reaction has stereochemical consequences. Groups on the dienophile that are cis to each other must still be cis to each other in the alkene product, in the cyclohexene product. Similarly, groups that are trans to each other in the dienophile must still be trans to each other in the cyclohexene product. All right, questions? Yeah.
This is kind of unrelated to this, but in the study guide, you had us do intra-Solomons reactions with the reactive cells.
Okay.
Is that something that we like Toro or what's something we do with that?
So I think that in the study guide you do a reaction, a Diels-Alder reaction that happens in an intramolecular fashion. And yeah, you should be prepared to deal with that. I think the useful thing to do is just to be able to look at, first of all, in solving such questions, don't be afraid to simplify the molecule, because the core changes in the molecule are always just as simple as shown here. Everything else is substituents. And if you remember things about cis relationships in the diene or the dienophile being a part of the final product, that will get you a long way. Another thing you can do is to work on sort of what's called retrosynthesis of Diels-Alder products, where someone draws you a molecule and you have to try to figure out what the diene was and what the dienophile was. So I'll give you an example of that. Here is a molecule that was made via a Diels-Alder reaction. And you're supposed to think backwards into what was the diene and what was the dienophile. When we do this together, it's going to seem obvious. When you're alone in the testing center in the fog of battle, it will no longer seem obvious. So what you have to do is focus in on the key things that make a Diels-Alder product. First, identify the cyclohexene ring. 6-membered ring with a double bond in it. Highlight the double bond. That is, by definitions, carbons 2, and used to be carbons 2 and 3 of your diene. Once you know that, you know what carbons 1 and 4 of the diene were, and you know that these are the 2 sigma bonds that you made. With that in mind, you now know this is purple carbon 1 and purple carbon 2. We can highlight things if that makes it easier. So, and now I know that my product, because I know the Diels-Alder reaction, I know my product has to have that basic core structure. I can map onto these simpler drawings the atoms 1 and 2, and purple 1 and 2, and orange 1, 2, 3, and 4. Now I should pay attention to the groups that are on carbons purple 1 and 2. They are trans to each other in that 6-membered ring. Therefore, they must be trans to each other in the starting material. Okay, and then how about the diene? What else do I need besides what I've drawn? That methoxy group on carbon 2, which would be here. Okay, yes?
Do groups like that methoxy group ever affect the diene?
Do groups on the diene ever affect the diene? Yes. Actually, the presence of this methoxy group makes the reaction faster and more efficient. One of the reasons for that is it makes the diene more reactive because this methoxy group donates electron density to the diene. Okay, we'll practice that some more on Wednesday. See you then.